Okay, hello everyone. This is section 3.7 lecture, the rates of change in the natural and social sciences. Before I start the lecture, actually, again, I just want to tell you guys, please be patient. This is new to me and to everyone. So please, guys, don't get panic. And everything going to be all right. Please give me a feedback about these lectures. And then tomorrow, I'm going to take attendance using the discussion board. And hopefully we can use another software so we can meet online to see how it goes. So, and then I'm going to update you guys. So let's start with the section 3.7, the rates of change in the natural and social sciences. Okay, guys, the difference quotient, so the delta y over delta x is equal to f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. And again, guys, when we said change in y over change in x, we talk about the slope. And then if you guys look at the picture on the right, so you see that we have 2 points, point P and point Q, okay? So if I draw a line that go past through P and Q, that line actually is a line of a secant line, and then the change in y over change in x, delta y over delta x, is going to be the slope of the secant line. So here again, guys, we talk about this at the beginning of the semester. So again, these line, the red line that goes past through the Q and P, this is a secant line, and then the delta y over delta x, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1, that's the slope of a secant line. But if we take a limit as delta x approach to 0, that means as delta x approach to 0, so that, and we take a limit, that point Q get closer and closer to the point P, and then we actually find the slope of a tangent line, and that's the derivative. So we talk about this at the beginning of the semester. So the delta y over delta x is the average rate of change of y with respect to x over the interval x sub 1, x sub 2, and can be interpreted as a slope of a secant line PQ in figure 1 that I showed to you guys here. So again, guys, the red line that goes past through the Q and P, that's the secant line, and the delta y over delta x is a slope of a secant line. But when we take a limit, that Q get closer and closer to point P, and that is going to be a slope of a tangent line. So let's go to the next slide. Okay, so now as the limit, its limit as delta x approach to 0 is a derivative f prime of x sub 1, which can therefore be interpreted as the instantaneous rate of change of y with respect to x. The other word is a slope of a tangent line at the point P, x sub 1 and f of x sub 1. So, and then using the notation, dy dx equal to limit of the delta x approach to 0 of the delta y over delta x. And again, guys, the delta y over delta x is a slope of a secant line, And then when we take a limit as delta x approach to 0, then it's going to be the slope of a tangent line, as I explained to you guys in the previous slide. So now let's do some problem. So example 1, the position of a particle is given by the equation S equal to f of t equal to t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. So t is measured in the seconds and s in meters. So I'm going to answer these questions A, B, and C. So the A, it says find the velocity at time t. And again, guys, when we want to find the velocity at time t, remember that I told you guys we take a first derivative. So take the first derivative, we find the velocity, and when we take a second derivative, we find the acceleration. So here I ask you guys find the velocity at time t. So I'm going to take a derivative of this function. So let me write the function so you guys can see it here. So the function is s equal to f of t equal to t cubed minus 6t squared plus 9t. Okay, guys, again, when I want to find the velocity at time t, actually, I'm going to take a derivative of this function. So the velocity at the time t is equal to derivative of the function with respect to t is equal to, so if I take a derivative of t cubed with respect to t, so it's going to be 3t squared minus, and then 6t squared. So again, if I take a derivative of 6t squared with respect to t, so it's going to be 12t. And then finally 9t, if we take a derivative of 9t, is just simply is 9. So the velocity at time t is going to be 3t squared minus 12t plus 9. So now let's do the part B. What is the velocity after 2 seconds? And then what is the velocity after 4 seconds? So again, I'm going to use part A answer. So part B is going to be the velocity after 2 seconds. So again, guys, I'm going to replace t with the 2. So it's going to be 3 2 squared minus 12 times 2 plus 9. So again, I'm going to use the order of operation. 2 squared is 4 times 3 is 12. Minus 12 times 2 is 24. Plus 9. So 12 minus 24 is negative 12. Plus 9 is negative 3 meter per second. So now I want to find the velocity after 4 seconds. So again, I'm going to says velocity after the 4 seconds. So it's going to be 3 times 4 square minus 12 times 4 plus 9. So again, I'm going to use the order of operation. 4 squared is 16 times 3 is 48 minus 4 times 12 is 48 plus 9. So 48 minus 48 is 0. What's remaining is 9. So it's going to be 9 meter per second. So now let's do part C. The part C, it says when the particle at rest. So when the particle at rest. So the particle at rest when velocity at the time t is equal to 0. So again, the particle at rest when velocity at time t is equal to 0. So the velocity after time at the time t is equal to 0. So in this case, is going to be 3t squared minus 12t plus 9 is equal to 0. So now I'm going to divide both sides of the equation by 3. So if I just do it, so it's going to be t squared minus 12 divided by 3 is a 4t plus 9 divided by 3 is 3 equal to 0 divided by 3 is 0. Now I'm going to factor. So if I factor, is going to be t minus 3 times t minus 1. So if I make each one equal to 0, so it's going to be t equal to 3 and t equal to 1. So thus the particle is at rest after 1 second and after 3 seconds, because again guys, t is a time at second. So the particle is at rest after the particle is at rest. The particle is at rest after 1 second and after 3 seconds. So that's it. So here's example 1. So now let's go to the next example. Okay, the Boyle's law states that when a sample of gas is compressed at a constant temperature, the product of the pressure and the volume remains constant. And again, guys, the product, when I said product, means multiplication. So the product of the pressure and the volume remains constant. So pressure times volume remains, means equal, constant, okay? So now the question is find the rate of change of volume with respect to pressure. Find the rate of change of volume with respect to pressure. So first, actually, before we want to find the rate of change of volume with respect to pressure, first we solve for volume. So again, the formula was pressure times volume remains constant. So again, if I want to solve for volume, so I'm going to divide both sides by pressure. This and this is gone. So it's going to be volume is equal to constant over pressure. So if I want to write it more convenient to when we want to find the rate of change of volume with respect to pressure, I can rewrite it as volume equal to constant times, I bring the p from denominator to numerator and change the exponent to negative. So it's going to be c times p to the power of -1. So now I'm going to take a derivative with respect to pressure. So I'm going to take derivative of both sides. So take a derivative of v is going to be derivative of volume with respect to pressure is equal to again, the C is a constant, and then because it's with respect to pressure, so I'm going to take a derivative of P to the -1. So it's going to be, I put the -1 in front, so it's going to be negative constant times P, and then -1 minus 1, so it's going to be -2. So negative C times P to the power of -2. And again, guys, I can rewrite this as negative C over and bring the P to the -2 to the denominator and make the exponent positive. So negative C over P squared. So dV dP, derivative of volume with respect to pressure, is equal to negative constant over P squared. Okay, so now we find that the rate of change of volume with respect to pressure. So now let me ask you guys this. What happens if P increases? Okay, guys, let's just look at my final answer. So if I increase P, so you see that the P is P squared, okay? In the denominator, we have a P squared. So if P increases and then we make it a square, that means the denominator gets quickly larger and larger. And as denominator gets larger and larger, the whole fraction gets smaller and smaller. And again, guys, remember, this is the volume. So as P, the pressure increases, as P, its pressure increases, since this is a volume, so I'm going to say the absolute value of negative C over P squared. And again, guys, since the pressure increases and we square it, the denominator get larger, quickly get larger and larger, and the whole fraction gets smaller and smaller. So as P increases, the absolute value of negative C over P squared actually decreases. So the volume, is decreasing more rapidly at the beginning. Okay, guys, that's it. So this is the end of the lecture for section 3.7. Again, guys, please be patient and please don't get panicked. I'm going to take care of you guys, and I do my best. So right now we're done with the section 3.5 and 3.6, and then now I'm done with the 3.7. Tomorrow I'm going to I already post discussion board, and then tomorrow see if I can use either Zoom or the Proton, and then I'm going to let you guys know to see how it works. And we talk to each other and we use discussion board. I ask you some question, and I want you guys to work with each other to receive to that answer, and that you guys can double check the answer with me. And again, guys, make sure everyone be online at 5:35. So I'm going to take attendance. So again, guys, please be with me, love each other, take care of each other at this hard moment, and hopefully we can get over it very soon and we get back to our normal life. Thank you so much, and God bless you guys. Have a wonderful day.